Welcome in the second part of software design. This is the last theoretical lecture. Uh, Today lecture we explain for you the control hierarchy, structural partitioning, functional independence, cohesion, and coupling. For the first concept, control hierarchy, also called program structure, represents the organization of program components, modules, and implies a hierarchy control. That is mean when we construct the programs, the software consists of many components and many modules. How these models can be organized. Uh, this we mean by control hierarchy, the organization of the program modules or program components. It does not represent procedural aspects of software such as sequence of processes, occurrence or order of decision, or the repetition of operations, nor is it necessarily applicable to all architectural styles. As you know, in the programs, in the software, there are many components relevant to the sequence of the processes. What are the first sequence in the program? What are the first process in the software? How the actors can be interacted uh, with the system? How the if statements can be organized? How the loops, we mean by repetition, the loops operations, how can be conducted in the software? All these called procedural aspects of the software. Uh, the control hierarchy will not concern with the procedural aspects of the software. It concerns by the component include these procedural aspects. For example, module 10, which include the loops. How this module or how this component can be organized in the hierarchy. Okay, I can explain for you by let us open. For example, where is the brushes? This is the brushes. Let us take color. For example, this is the hierarchy of the software. And there is one module called module 10. This is M10, which is a part of the hierarchy. If these are the modules of the hierarchy, and for example, what are the position of this module in the hierarchy? And this module includes the loops, which is a procedural aspect, which is a procedural issue. The control hierarchy will not concern by the loops, how the loops can be organized inside the module, rather than concern by the module itself, how can be organized in the hierarchy itself. Okay, this is what we mean by control hierarchy. And this is an image as here. If we take print screen and put where is the pen, new, paste. This is represent the hierarchy here. Where is the brushes? This is the hierarchy. That is mean the organization of module. The hierarchy start by module 1. This is the first module. I can give you an example. For example, now if you open BOC website, it will appear for you at first only one interface. This is the first interface in the module. This is module 1, which represents the top of the hierarchy. And there are many other modules connected to the top of the hierarchy and degrade down, which is degrade vertically and degrade horizontally. Here, for example, the first level consists of 3 modules, and each module includes other modules. This is level 1, level 2, level 3, level 4, level 5. The designer or the software engineering team who decide how many interfaces or how many components connected by each level. For example, open our software to give you a practical example. Where is software student info? Student info is a hierarchical organization. That is mean start by only one module. By only one module. Because I opened many applications, my computer, it seems slow. Run the software. The software consists of many interfaces, and think about these interfaces as a component. Think about this is the first component in the software. What are the modules connected with these interfaces? How many? There are 2 modules. If I click here, it will be student login back. If I click here, it will be the admin login. That is mean the hierarchy return to our brushes. The hierarchy of our project starts by one component and degrade the second level include 2 components. Here, student login and admin login. Here, this can be A, this can be B. And also, student login can lead to you to another component. And admin login can lead you to another component. Also from the second component, from the third component, after, for example, if you go in this direction, student login, and transmit to the interface after login, which is student operation. You can, in this form or from this form, you can put another form here in the same level. The distribution of the components in the horizontal called fan out, and the distribution of the component in the vertical, in the depths, called fan in. That is mean fan in represent how many components from the beginning, from the started component to the end. And fan out horizontally how many components in the specified level. For example, here in Pressman example, we have three components. In our real design, here we have two components. If we open here, we have two components. Only we have two components. But we can put another button here, and this the third button can lead us to different interfaces. Here, this is student interface. It is different from admin interfaces in the components, in the tools, in the look of the interface, and so on. This we mean by the fan in and fan out in the control hierarchy. Depths and widths provide depths, that is mean vertically, and widths represent the horizontal level, provide an indication. Indication, that mean indicator of the number of levels. I said that the designer or the software engineering team who decide how many levels in this software. If we return back, now you can find how many levels. We have about 4 levels in our this project. If I open, yes, this is the first level. The first level include only one component. The second level include the login. The third level include the information about the students. The fourth level include, for example, the search operation after that appear after the or during the execution of the operations. And we can increase in the depths or in the widths, in the depths or in the widths. We say that depths and widths provide an indication of the number of levels of control and overall span of control, respectively. That is mean level after level. Fan out is the measure of the number of modules that are directly controlled by another modules. In the horizontal level, the top component control the below or the bottom components. For example, if we return here, this is the top one, and in the first level, in the second level, in the horizontal, we have 3. These 3 components controlled by the first one. This we mean by the controlling of the because if we delete this component, also the second level will be deleted because we delete the control module or the control component. Structural partitioning, also this is a concept relevant to the hierarchy. If the architectural style of a system is hierarchical, the program structure can be partitioned both horizontally and vertically. When we talk about horizontally architectural style or the architectural design, we say that there are many styles for architectural design. And one of them is structural architecture design or structural architectural style. In this case, the components can be organized in a hierarchy. And in this case, the components can be partitioned. Partition, that is mean divided into small modules and distributed horizontally and vertically. Referring to the figure, this is the figure. Uh, these are the partition components from the software. The software engineering team decide how many part or how many module in the software or in all the software, and then distribute this in a hierarchical context. Here, this is another organization. For example, here, this is a component function 1, function 2, function 3, and function 1 includes this organization. Function 2 include different organization. For example, here, one component connected with 3 components. Here, one component connected only with only one component. And the second, like the previous one, connected with 3. But here, the third one, like our project, there is only one starting component, and then there are 2 components. Here, this is admin login, student login. Admin login can lead to student information and can lead at the same time back to the login again, and so on. The partitioning the structure horizontally provides number of distinct benefits, advantages. There are advantages from dividing the software into components or into small components. Software that is easier to test. We said that the software engineering team who design will not conduct the testing. The testing will be conducted by another people. And when those people found the software is partitioned into small components, it is easier to be easier to be maintained. How easy to be maintained? Because we fix only the modules that include the problem. Fewer side effects. That is mean if we have an error, the error will not propagate to the other components of the software. It will be restricted only in that module. Software that is easier to extend. Yesterday we talked about extending the software. Here, this is our software. And we said that because this software consists of many components, can be easy to add. Extend, that is mean to add new components. It is easy now for our software to add new components. That is mean to extend, to maximize the size of the software by adding new components or adding new functions. Because measure functions are decoupled from one another, change tends to be less complex, and extensions to the system, a common occurrence, tend to be easier to accomplish without side effects. When the negative side, horizontal partitioning, often causes more data to be passed across module interfaces and can be complicated the overall control of the program's flow. Here, it will be advised to decrease the coupling because uh, the more horizontally, that is mean, if we put in level 3, for example, more components, that is mean we can increase the probability of intersection of data, and the level or the software will be complicated, and it will maybe it will affect the flow of the program or the control of the program flow. Functional independence, a new concept in the also in the software design. The concept of functional independence is the direct growth of outgrowth of modularity. That is mean this concept relevant to the modularity. When we talk about the modularity, we say that we divide the one software in many subsystems, and then integrate these systems in one software and give specified these divided parts called module, and give each module a specified function. This is specified function called independent function. The independent function, that is mean the module will not do other function. For example, here we implement this in our project. Login. This is one of the module or one of the component of the software. For example, this is module 2 or module 3. The function, the basic function of this module is login and register. We have two operations. The advice is recommended to be only one function, register or login. Let us log in as admin. Here there is no registration here. This is better than the student login component. Why this is better? Because it includes only one function. There is no other function. Here in student login, we have two functions. Register, login. We must to put registration in independent component or independent interface, and then in another interface put login like admin login here. Okay, this is what we mean by the independent or functional independent, to give the module a single function. Functional independence is achieved by developing modules with a single minded. Minded, that is means there is no other direction, or there is no other function, and version to accept the interaction with other module. Why this concept is important? Because we want to design software so that each module address a specific subfunction of requirements and has a simple interface when viewed from other parts of the program structure. You will design the software for the customer. Suppose that return to our customer, to our software. For example, this software, the customer of this software is Bremen University College. BUC. When they ask you about the functions, in the communication, you say that we will make a software that lets the student register their courses or register in the college. They will ask you, where is the registration? You said, yes, here is the registration. Where is the login? Yes, here, this is the login. When it is better when the customer asks you about the functions of the system, to give these functions independently. When they ask you from the login, yes, this is our login. Where is the registration? This is our registration. Where is the operations? This is our operations, and so on. Okay, this is the benefit of or the importance of uh, uh, functional independence. The other important concept is the cohesion. Cohesion is a natural extension of the information hiding except described. Uh, One of the basic characteristics of object-oriented programming is the information hiding. Information hiding, that is mean the attributes of this class cannot be accessed from outside of the class. And when you design the assignment to, we learn how to distinguish between the attributes in the class and the method of the class. We said that we put minus sign in the attributes to refer that this cannot be accessed from outside. And we put plus sign in the class methods to refer that this can be accessed from another class. The cohesive is relevant to the information hiding. That is mean is relevant to the attributes of the object. A cohesive module performs a single task within a software procedure. Also, this concept relevant to the data, the functional or the module independence. That is mean if you have many modules, a cohesive means that is mean this module will not accomplish or perform more than one functions, requiring little interaction with the procedures being performed in other parts of program. Stated simply, a cohesive module should ideally do just one thing. That is mean, as I referred before in our student information system, we said that you must to let the interface to perform only one thing, only one function. Okay. The last concept is coupling. I think that we practical on this component by in our design in the second practical lecture we learn how to couple between the software components. It's the measure of interconnection. Interconnection, that is mean the internal connection of the components. Here, if you look in the left side of the project, our practical project, you found many components. Form 1, login interface, program CS, student information, student registration, student information 2, data set 1, How many? 1, 2, 3, 4, 5, 6, 7. And now we intend to extend this. The interconnection, the internal connection between these components called coupling. For example, how we can move, how we can transmit from one component to another component. You see in the programs, we control what will be the first. Now, form 1, it will be the first component that appear to the user. This is a part of coupling. But in our previous practical lecture, we changed the form 1 many times. Now, if we run stop debugging and run, this is the first page, first component appear for us. And you will decide what are the next level of the interfaces of the components must be coupled with this. Also, if I can easily change this, for example, here, where is programs? This programs, and for example, put the last interface that we designed, student information 2, student information 2, this student information 2, run. You are the designer. The designer will decide what is the first component in the system. What is the first component in the hierarchy? For example, I need the student. I need from the students to go directly to this component, this part of the software. No need to go to the first page. No need to let them enter their username and password and so on. This we mean by coupling. Coupling is the measure of interconnection among modules or components in the software structure. Coupling depends on the interface complexity between modules. In each software, there is a complexity. How many interface, how many components, how many modules connected with this interface? How many modules connected with this module? This is called interface complexity or component complexity. The point at which entry or reference is made to module and what data pass across the interface. For example, here in our system, return to form 1, stop debugging, form 1. Where is form 1? This is form 1. Run again. Here, they are second levels that we can join or we can couple with this level. For example, here, you will decide from the previous level what are the information must be in this level. Okay, this is we mean by the information passed between level and between level and level. Okay. Now we are finished our lecture. We will see if you have questions. I can answer you. Any question? You ask something? Okay. If there is no question, I will stop recording and return back to you. This is our project. Stop recording.